Okay, sorry about that. In the last video, I was going on and on about problem number 5, and then I ran out of time and my video cut off. So um, let me just return to that for a moment, and let's just go ahead and graph this function. So we actually already did, I guess, didn't we? Or did we? I can't remember. I guess we didn't. We're graphing 8x sine x. Okay, and I'm going to graph this from minus 15 to positive 15, as the problem suggests, just to get a handle on what in the world I'm looking at here. And I'll do zoom fit with that. Now notice all these questions are about smaller intervals, but nevertheless, so we've got this very curvy graph, right? Lots of bends. So if I look at the interval from 1 to 3, actually before I do that, well, no, I guess we'll go ahead and do it. Okay, 1 to 3. So over that portion of the graph, I can tell I didn't do zoom fit, I just hit graph. Maybe I should have done zoom fit, but you can still see that from 1 to 3, in fact, why don't we do the zoom fit? That it's actually, we've got a picture kind of like that. So I see that the maximum actually occurs within the interval. So, but the minimum does not. I'm sorry, the minimum, well, let me rephrase that. The maximum vertex occurs within this interval, but the minimum is just going to be this bottom value down here. So here I can use calc max, but I cannot use calc min here. Okay, so I'm going to use calc. So part A says find the minimum value. It's just going to be the value of the function at the rightmost point, and I just inspected the graph to get that, and so that's 3.386. Now the maximum value from 1 to 3, for that one, I actually am going to use calc max. And I'll move to the right, I'm sorry, to the left, and then I'll move to the right and calculate my maximum, and there's my maximum value. 2.028 x coordinate, 14.557 y coordinate. So this includes the vertex, which is a maximum. Now if we go to 4 and 9, which is the next series of questions, 4 to 9, and we do zoom fit with that, let's see what kind of portion we have there. So from 4 to 9, we've got a little bit more happening. We've got the minimum is a vertex and the maximum is a vertex. So we actually, in this case, we will use calc minimum and calc maximum for both of the, for calc minimum here and the calc maximum there. So to find the minimum value here, I'd have to use calc min. Here I would have to use calc max. Here I use calc max. But for the first one, just to recap, I didn't. I just used y1 of 3. Okay. Now, I'm assuming that everybody knows how to do these things. I hope you do. Use these procedures. I just want to talk about kind of what procedures we need to use. So if we look from 12 to 14, which is the last two parts, and again, I'll do zoom fit, and it's going to be the same scenario. We're going to have to judge what sort of picture we have. So over this region, the minimum is going to be y1 of 12. And the maximum, to me, I think it's pretty clear that the maximum is going to occur. And if you're unsure, you can always hit trace and just kind of follow. Oh, what did I do? I moved my graph, I'm sorry. Hit trace and follow along to make sure that you're not deceiving yourself. but I think that the maximum is going to be at the rightmost value, so y1 of 14. So 108.58, 109.86. You see I'm still going up, and 110. And so at 14, that's going to be my biggest value. So y1 of, let me go back to this. So y1 of 12 here, and y1 of 14 here. Okay, so I'm leaving you to actually carry this work out, but that's just telling you how to do it. All right, let's move on to number 6. Let f of x be a 15th degree polynomial with a negative leading coefficient. True or false? Okay, so what's the range of this? Well, if it's an odd degree polynomial with a negative leading coefficient, we can say a couple of things about this. In general, we can say that's an odd degree cubic. Sorry, that's a cubic with a negative leading coefficient. And then if I go to, that's third degree, if I go to the 5th degree, it's going to have another bump, but it'll still basically look like this. So it's going to be going, as we move from left to right, it's going to go down and then down some more. So my range is in fact going to be all real numbers. So this is true. How many intercepts could we have? How many x-intercepts? Well, let's go back to this picture. Well, actually, I haven't drawn a 15th degree polynomial. But it would basically have a whole bunch more bumps here. But remember that the number of intercepts is related to the degree of the polynomial, so it can have at most 15 x-intercepts. So like for a cubic, the most you could have is 3. So if that was your x-axis, that'd be 1, 2, 3, and so on and so forth. So for 15th degree with 15 intercepts. Turning points, at most we could have 14, and inflection points, at most we could have 13. So this is just using these formulas. The number of turning points is at most degree minus 1, inflection points is degree minus 2, and intercepts is degree. Okay. How about E and F? On the far left-hand side of the graph, before the first turning point, what is this thing going to be doing? Well, so really it doesn't matter how many bumps it has. We're just looking at this region over here. So from this region here or here. And in both cases, we are decreasing at a decreasing rate, concave up. So that's decreasing at a decreasing rate, and the graph is concave up. On the far right-hand side, what are we going to do? Well, again, the picture, we just need to look at this region or this region, in which case we are again decreasing. And my picture is not the greatest, actually. Let me draw another one. So we'll be talking about something like this. And so we are decreasing at an increasing rate and concave down. So that is decreasing at an increasing rate, concave down. Okay, that completes number 6. Let's move on to number 7. The population of the Midwest region of the United States for the census years 1900 to 1960 is given by the table below. And then we want to find the best fitting quartic function. That's a 4th degree. And then do a bunch of stuff with it. So I tell you what, to save me a little bit of time, I'm going to enter this data off camera. Alright, so I just went ahead and entered all this data into my list editor. There it is. And now we're going to find this quartic regression model. So let's do that. So we'll go to Stat, Calc, Number 7 is quartic regression on L1, L2. Save it as Y1. And there is our function. Okay, so just to make sure you don't misunderstand with these coefficients, sorry, I'm trying to move the calculator out of the way. If we wanted to write down the model, this first value, notice it says, let me change my color there, A equals 7.04 and e to the minus 6, or e minus 6. What that means is that the A coefficient is 0.00345 704. 1, 2, 3, 4, 5, 6. That's scientific notation. So the first term of the polynomial would be that. Okay, now I rounded a little bit, but nevertheless, that would be the first term, and then it would be that, and then b would be, actually that's a negative, so it would be minus 0.0007 not another point, 717 x cubed, and so on and so forth. Okay, so that's just a little bit about what that would actually be your quartic regression model. All right, so part B, let's go ahead and find the SSE of this. So that would be second list math sum, second list resid squared. So our SSE is 0.991, 0.9906. And then our average error will be the square root of the SSE divided by the number of data points, which is what? 1, 2, 3, 4, 5, 6, 7 data points. So that's our average error, 0.3762. 0.3762. The coefficient of determination, remember we don't have a correlation coefficient here, we have a coefficient of determination. So we go to stat, I'm sorry, no we don't, we go to VAR's statistics equation, and then scroll down to capital R squared, which I skipped. There it is, number 9. And my coefficient of determination is 0.9978. And what percent of the variation in the data is explained by the quartic model? Well, that would be 99.78%. So we just take the coefficient of determination and put it into percent form. All right, what about H? Does the model under, over, or exactly predict the 1950 population? So the 1950 population is 44.5, and my model says, so 1950, we can just put it, because this is from 1950 to, or 1900, so just make sure you get the correct elapsed time, which is 50 years, as you probably knew already. And that's 44.187, 44.188 actually. So this is, actually let me write it up here. 44.18 is predicted, and so it is smaller, so it underpredicts. The model underpredicts the actual population. Use the model to predict the population in 1970. Okay, so we're extrapolating there into the future. So that's a simple y-vars question, and our elapsed time is 70 years. So that'd be 68.14. And the last parts of this question we'll have to finish in the next video.